Okay, hi everyone. Let's see. I'll share my screen. Yeah. Okay, so let me know if you can see my screen. I'm looking at the chat. Currently, I don't see any messages. So maybe we'll just go ahead and start. If anybody can see, so please let me know. We will just wait another minute or so for people to join. I'm not sure how can I see if people are here. Okay, perfect. Thank you, Thomas, for confirming. Great. So let's just go ahead and start. So thank you, everybody, for joining. My name is Guy Salton. I work at the company called Run AI. And session today, we'll talk about Kubernetes for AI workloads. So we'll also have a few short polls to see the familiarity of the audience with Kubernetes, which I assume that most of you are familiar, at least in some way. And also for AI, I know that this conference is not really, the focus is not really AI, but we might have some people that know. Anyways, I will explain everything from scratch, so don't worry. So a bit about the agenda. We're going to talk a bit about AI and how it's also adopting containers. So containers are also being used in the world of AI and deep learning. We'll then talk about how Kubernetes can be used for AI workloads, and we'll see what you can already do with Kubernetes, and that works pretty well, but still what are some missing capabilities. Again, we'll see that Kubernetes was not really designed for running AI workloads and for training deep learning models. However, with some work, it can be a pretty good solution for it. So let's start. First, as I mentioned before, the AI ecosystem is being now built around containers, and like in the world of software engineering, that containers are being adopted for a few years now, and everybody sees the advantages of using containers. This is happening also in the AI ecosystem. So, for example, on the left-hand side, you see the NVIDIA NGC, which is a registry of pre-trained models for AI on Docker containers. So like probably most of you already know Docker Hub. This is also a public Docker registry in a way, but with Docker images that are built for AI, that contains AI frameworks and are designed for training AI models. Also, in terms of the data science community, all of these tools that you see on the right-hand side are built on top of containers. So you can see projects here like Argo that some of you might be familiar with, Kubeflow, which is a data science platform that was built around Kubernetes. So the AI ecosystem is adopting containers. And regarding Kubernetes, as you know, it's currently the standard container orchestration. And maybe I'll just launch a quick poll, and we can see your familiarity with Kubernetes. Again, I assume that most of you are familiar with it, at least a bit. If you can see the poll now, you should be able to see it. Yes, and we see that, yeah, we have a few votes already, and we have some people that are very familiar with it and some that not really. Okay, so that's good. We have different levels of familiarity with Kubernetes. Maybe I'll just talk about it briefly. So Kubernetes is a container orchestration platform for those who don't know. So when using containers, especially when deploying, microservices applications, you would usually need to orchestrate multiple containers for multiple microservices, and Kubernetes can orchestrate these containers to work together, communicate with each other. It's also portable, so you can deploy it on different environments, both cloud and on-premise. It can be composed by YAML files, which is also now very adopted and known in the DevOps community. And it's also scalable, so it's designed for scale. It can be easily scalable, especially on the cloud, to add multiple servers and then scale and support more load. And Kubernetes is now, again, de facto the new standard for container orchestration for the software development world. However, for AI workloads are pretty different. So as opposed to microservices that are deployed, again, as services that should run forever, and they should then be scalable, and they should accept requests, right, and support them for applications. AI is a bit different. So a bit about the world of AI, and maybe we will launch the quick poll about AI before we continue. I just want to see again your familiarity with AI. So I'll publish this poll quickly. You should see it now. And let's see if we get some results. And it's completely fine. I wasn't counting on anybody to be very familiar with AI, but just want to see what we have in the audience today. So we'll just give you a few minutes and then we can continue. Great. Yeah, so this is pretty much what I was expecting. Again, this conference is not really focused on AI, and that's completely fine. So let's go and share again. Sorry, go back to my slide. So anyways, with AI, just in general, of course, we won't go too deep, but we'll look at it more for like the DevOps point of view. So with AI, you have some model that you built. It can be using different frameworks. Maybe you've heard about PyTorch or TensorFlow or Keras. Then you kind of build this model, and then to make the model actually work and be ready for production, you have to train it. And this means that you need to provide some pretty large data set, and you need to run the model and use this data set, and then it will then consume the data. It will try to predict, and give the correct results. And then based on the results of each execution, it will improve itself and learn. And that's how, in general, like this AI and deep learning model works. And for running this training job, in the world of AI, it's not running on regular CPUs, because this will take a long time. Large deep learning models, if you try to train them on CPUs, it can take long days, even weeks sometimes. And for that, there are different accelerators. And maybe some of you have heard about GPUs, graphic processor unit, that was originally designed for maybe gaming, but now are being very adopted and used for AI, because they can run these large training jobs much faster. So AI models are trained on these new accelerators on GPUs. And also, again, the type of the workload is very different from regular microservices, because it's not long running or like forever running services that accept requests. These are workloads that run to completion. We need to start them. They need to do the training. Once the training is completed, they should terminate and finish. So Kubernetes was not really designed for it. However, we'll see what you can already do with Kubernetes, which is pretty cool, I think. So we'll go to a demo part now. I'll share my screen. We'll see a Kubernetes cluster that I spin up, and then we'll run some AI deep learning training job together, and we'll see how this is being done. So for that, I will open my terminal, and here I'm inside some machine that has Kubernetes installed on, so I can go and run the kubectl get namespaces, for example, ns. It will show me all of the namespaces that I have on my Kubernetes cluster. Again, I won't explain everything about Kubernetes from scratch. Like we assume that some of you are already familiar with it. So what companies that want to start doing AI and using containers, we usually do is they will have a namespace for every research team, right? And they will have maybe a few researchers on each of these teams, and they will then purchase these GPUs. So their researchers can go and train their models. The thing is that these GPUs are very, very expensive. So usually they would start by purchasing maybe just a few GPUs on premise, or they would start some cloud-hosted Kubernetes cluster that has a few GPUs, and then they would want to assign these GPUs to the teams. Now, to avoid starvation, meaning you don't want one team to use all of the GPUs, then the other team won't be able to run any jobs. What you can do with Kubernetes is to define something called a resource quota. So if I run the kubectl get resource quota, you'll see that I have a resource quota here, and this is an entity of Kubernetes, and we can go and look at what this resource quota is. I actually added in a YAML file, so I can go and have a look. Okay, so this is a simple Kubernetes resource, like you can see here. It's called resource quota, and what it does is that it can go and limit the amount of resources that can be used by a specific namespace. So you can say in the metadata which namespace you want to limit the resources for. You give this resource, the resource quota entity, a name. For example, I can call it GPU quota. And then you can say that this namespace can only use one GPU, for example. If I look at my actual machine here, I can see I'll run some command. Don't really worry about this command. I just want to show you the specs of my machine. This will show it to me clearly. So I see I have one machine here, and this is my all Kubernetes cluster is deployed on one machine, and I have 8 CPUs on this machine and about 30 gigabytes of RAM memory, and I have 2 GPUs. Okay, so I have 2 GPUs, and I want to assign one GPU to each namespace so that each research team can consume only one GPU. Okay, so this is what I'm doing with this resource quota. Okay, I have 2 namespaces, one for each research team, and for each of them I applied this resource quota that is limiting them to use only one GPU. Okay, and now let's go and see how we can, we created some Docker image that can then be used for training my job. So let's quickly go to the browser and have a quick review of this Docker image. So just like you are familiar with any kind of Docker containers, I created some example container here that is designed for training a deep learning model. So you see that the base image is from NVIDIA. It's using something called CUDA. This is some framework that is being used with deep learning. And then it specifies all kinds of environment variables. It installs some dependencies, some packages that are required that relates to my deep learning framework, something called TensorFlow and Keras. We won't go too deep into this. And it will then go and copy some data. This is some data called CFAR10. It's a bunch of images that we will load into the container, and it will use this data to train, to learn. And then it will also copy some entry point script. And once it will start, it will run some Python file and start the training. So this is the entry point. Once we will start a container, it will automatically go and start training my job. We can quickly go and look at this entry point. So you see it will go and run my Python file, and my Python file contains my actual deep learning model code. So it's using Keras, if you're familiar with it, and it's then going to use and have some pre-processing on the image. It will be able to load this data and then run the training. So again, we won't go too deep into this Python code, but this is what my container will do. Okay, so this is my Docker file. I built this image and I pushed it to a Docker registry in Google, in GCR. And what I can do now is I can go back to my terminal, and you can see, first of all, that if I run Docker images, I need sudo Docker images, and I will see this image here. I should see it here. And it's called quick start. Yeah, maybe I need to pull it first, but no, don't really worry about that. We will go and then look at the Kubernetes resource that will go and then use my image to start the training, and that won't be. Okay, let's see. My terminal got stuck a bit. Go back to my machine. Now, as we said, because we need to have some job that will run to completion, what we need here is not really a deployment in Kubernetes or a pod, but there is a resource in Kubernetes called a job, and that's what we will need to use. So I created some job and Kubernetes job, and we'll see what it means, a Kubernetes job, and then we can go and quickly run it. Let's just see if my machine seems to be okay. Now I'm inside. Okay, great. So let's go and go to this directory here. And inside here, I have a few files. So we already saw the GPU quota. This YAML, this is what defines the quota of GPU, where I'm going to limit how many GPUs will be used by each namespace. I can then create a role and a service account and a role binding. And I won't go too deep into this, but this is just if you don't want your users, right? Let's say I have users, I have my researchers, and I want each of them to be able to only use one GPU because I want them, I don't want them to use all of my expensive GPUs and then don't leave any for the other researchers. What I can do in Kubernetes is create something called a service account. This is what defines my user. So for example, I created this user called Team A user. It belongs to a namespace called Research Team A. And then I can create a role for this user. So, then I allowed him to go and run jobs, and he can run different resources, and he can use different AI groups, but then I can create a role binding that binds my service account, my user definition, to the role. And what this means is that this user will only be able to run pods and jobs on this specific namespace. He won't be able to do it on different namespaces. So this is how I can assign resources to specific users, by assigning them to a namespace and then limiting the user to only be able to run jobs on this namespace. Hope this makes sense. Now, the last file that I want to show you now and then run the job is this AI job YAML. So if I look at this job, this is a resource of Kubernetes called a job. Again, it's not a pod, it's not a deployment, it's a job. A job is a resource that's designed to run to completion. So like a pod, I can go and assign it to a specific namespace, and I can then, under the spec here, choose which Docker image will run for this job. So I have this quick start image. This is the image that I built from the Docker file that I showed you before. So this image already contains my deep learning framework. It contains all of the dependencies. It even has the actual code, right, the Python code that I showed you, as well as the data baked into it. And it has an entry point. So once the container will start, it will just start training my deep learning model. And once it will finish, this is the definition of a job in Kubernetes, then the pod will just be automatically terminated. Now I can also limit the resources of this job to 1 GPU. So again, you see this is something called extended resources. So unlike CPUs or memory, I can say I want this job to be limited to using only 1 GPU, okay? Now I can go and apply this YAML file to run the job. So let's go and run the kubectl apply -f to pass the file, and then say that the name of this YAML file, right, is called AI job. So once I apply this YAML file, a job should now be created in my namespace. So I can run the kubectl get jobs. And I see that now I have a new job here. It didn't complete yet, right? It only started now, 10 seconds ago. And if I look at the pods in my namespace, I see that a new pod was created. So a job will go and actually create a pod or multiple pods if needed, and then the pods will go and actually run the work. So if I go and look at the logs of this pod, right, that my job created, I can run kubectl logs, and then the name of the pod, and I can add the -f to follow, then I will see that it's now running, right? I think one of them got an error. This is also some characteristic of a job. If a job starts a pod and then the pod has some issue, it will automatically start a new pod. And this is actually pretty good for availability. So let's go and look at the logs of this pod. And this can happen. You can have pods that will fail for some reason, then the job will take care of running a new pod instead. So I see that now this looks good. It goes and prints the amount of resources that it's going to use. It's going to run on 1 GPU. And soon I will see these epochs in my logs here, and this will show me that my model is being trained as we speak. So this looks okay, and now the training job is running. Yes, this looks good. I will see these losses. This is what shows me the accuracy of the model, and it will go and improve over time as it learns. So this is how it works, and this can take maybe a few hours to finish. So I just want to show you how these can be launched. Now you'll also see that if I try to delete this job, I will go and run not delete the job, delete the pod. I will go and try to delete the pod. It will be deleted, but if I will go and look at the kubectl get pods again, I will see that a new pod was automatically launched by the job, because again, the job monitors the actual pods that are running, and if it sees that there was some error, maybe one pod is being deleted, it will go and launch a new pod automatically. So this is something very good for Kubernetes, that it has this capability out of the box, to make sure that we are running, and if there was some issue, it will just launch a new pod instead. If I want to completely terminate this job, I can go and run the delete job command and say I want to delete this job 1. And then if I go and look at the kubectl get jobs, I see that I have no jobs now, and if I look at the pods, they should be terminated. Okay, so far we saw how to run a deep learning model to train it on Kubernetes. And now reminding you that we set a limit to the namespace. So if we go and now try to edit this YAML file and say, let's say I want my job to run on 2 GPUs instead of 1 GPU, I can do that here. I can change it to 2, and I can save this file, and then I can run the kubectl apply -f on this YAML file again. But what you will see is that if I look at the jobs now, yes, I have a new job here, okay? But if I go and describe this job, you will see that it got an error. It cannot start a pod. Why? Because it exceeded the quota, right? It tries to use 2 GPUs, but it has a quota of 1 GPU. So this is the limitation in a way, right? Because the DevOps that is in charge of the resources that bought these expensive GPUs, on one hand, he doesn't want to have starvation, right? He doesn't want one researcher to use all of the GPUs and then other researchers cannot do anything. But on the other hand, this means that if one researcher wants to use more than one GPU, he can't do that. He's limited only to use this one GPU. And in the world of data science, you'll see that sometimes, and we'll go back to our presentation now. So if we saw what does work in Kubernetes, right? But then what are the limitations? What are the issues? Okay, so what's missing? What's missing is that data scientists they do not really want to work like this. So here you can see, for example, graphs of real researchers, real data scientists, and how they use GPUs. And you can see that maybe they have some days when they want to use a lot of GPUs. Maybe they have a very big training job that they need to run. Sometimes this requires more than one GPU. Sometimes this requires a lot of GPUs. And then after they have a few days that they're using a lot of these resources, very expensive resources, they might not use any GPUs for weeks. So having this static allocation of GPUs for each user is problematic, because if you think about it, they won't be able to do this. They won't be able to run on a lot of GPUs for one day because they're limited to only one. And on the other hand, while if you have static allocation, then if one researcher doesn't need any GPUs for a few days, the other researchers cannot use it. Okay, so these are like the main limitations of Kubernetes when trying to run AI workloads, is that there is no real automatic queuing and dequeuing capabilities to the scheduler. So if you're familiar a bit deeper with Kubernetes architecture, there is something called Kube Scheduler. This is the component of Kubernetes that is in charge of scheduling the pods on the different nodes, right? So Kubernetes cluster might have multiple nodes, multiple servers. Each server will have resources. It will have CPUs and memory and maybe GPUs. And the scheduler is the component that will look at a new pod that tries to run. And let's say this pod can ask for a few CPUs and maybe one GPU, etc. And it will look, then the scheduler will look at which, if we have a node available that can answer these requirements. And if not, then the pod will not be able to be scheduled. And if there is, the scheduler will schedule it on a pod. But again, there is no it's really a way to define priorities or policies to different users. There is no way to have a dynamic kind of allocation and preemption of jobs. So a bit about the history of AI, before AI, and also today, there is the world of what's being called HPC, high performance computing. And this has been around for many years, and it can be used for many different type of calculations and very large jobs that might need to run on very, very sophisticated and complicated and expensive hardware, and run on a lot of resources in parallel. And these kind of legacy tools, they have all of these capabilities, but again, Kubernetes was not kind of designed for that. So a few of the main challenges is that Kubernetes is what we call scale out and not scale up. Okay, and what this means is that, like we said before, Kubernetes was kind of designed for running, let's say, millions of services that needs to have high availability. They need to be scalable, and they are designed to accept requests. However, AI workloads are scale up, and this means that for a system that wants to run AI workloads efficiently, it needs to support large distributed jobs that will run on multiple resources and can coexist efficiently with small workloads that require fewer resources. And so there are different type of capabilities that are ideally required, like bin packing and consolidation. This means that the scheduler, in a way, if it was more designed for AI, it should have take into consideration that maybe a node has a few jobs already running on it. Then if there is a new job that wants to be scheduled, make sure that it will schedule it on the same server that is already being used, to avoid defragmentation. So there is also a performance importance for jobs to run on the same server and then free up other servers for large jobs. And there is also a concept called elasticity, for example, where maybe a job, if it has, let's say, 4 GPUs to run, it can run and finish in an hour, but it can also run on 2 GPUs. It will just take it a bit longer to run. So if the scheduler was smart enough, it could have then designed the job to start on maybe 2 GPUs. Then if there are 3 GPUs in the cluster that other users are not using, it can expand and use more than these 2 GPUs. And if, again, based on other priorities, these 2 additional GPUs are not yet available, not anymore available, then it can go and shrink back and use only 2 GPUs. There is also something called gang scheduling. This is for very large distributed training, meaning that, let's say, you have a few servers in your Kubernetes cluster, and each of the server has 2 GPUs, but you want to run a large job that needs 4 GPUs. You need to run across servers. So this means that you need to have some kind of synchronization capability to start multiple pods on multiple servers that should run together and then finish together. And then if there is any issues, they should be paused together and then resume together. So these are all kinds of capabilities that Kubernetes does not yet have. The second challenge is scheduling for batch jobs. So just like we saw in the demo, usually for deep learning jobs, for training jobs for deep learning, these are jobs that run to completion. They're very compute intensive, right? They need very expensive and a lot of resources, but they run to completion on accelerators like GPU. And what is needed is that, first of all, we need to make sure that once such a job is completed, then it will automatically free up resources so other jobs can use these expensive resources. And we also need to have some kind of queuing mechanism and make sure that maybe we have one researcher that has very important and high priority AI models that needs to be trained. And then there are maybe some lower priority ones. So we need to have some kind of capability to give priority to one user and then have a queue. And based on the priorities, the scheduler should know which jobs to run first. Maybe if the researcher that has higher priority doesn't currently use any of the GPUs, then ideally the scheduler should allow maybe other researchers to use it. But then once the high priority user needs to use, then the scheduler should free up the GPUs for the higher priority user, and then send the jobs for the lower priority users back to the queue, things like that. And lastly, also something called topology awareness. So for topology awareness, this is a concept of there are 2 main kind of scopes here. There is something called internode communication, and also how resources interact within a node. So this is also, it can affect the performance and the speed of these very large jobs very significantly. So there is some internal topologies within the server between how the GPUs and CPUs and memory are all connected. So if the scheduler takes this under consideration, and it makes sure that if that we have a job that needs to work both on CPU and GPU, then it will be scheduled on GPUs and CPUs within the same internal topology. This can increase the performance a lot, but also with internode communication. Sometimes you will have very large jobs, like we said before, that will run on multiple distributed server in parallel, then these kind of external topologies ideally should be taken into consideration as well. So by the way, what we do in Run AI a bit is we try to apply the HPC concept, right? This high performance computing concepts with all of these capabilities that we just mentioned together to Kubernetes. So Kubernetes has its default scheduler, then again, was not really designed for it. So it can run jobs like we saw before. It can make sure that it will have this automatic recovery if a job scheduled the pod and then the pod is not currently available. The Kubernetes scheduler will then run a new pod instead. This job concept is something that is designed to run to completion. So this works nicely with AI workloads. And obviously, we saw that AI workloads can be packaged in Docker images. So the world is going in this direction. However, Kubernetes, as it was not designed for these kind of workloads, it does not yet support all of these different distributed computing capabilities. So once these are applied to Kubernetes, then this can bridge the gap and then have AI also work natively in the world of Kubernetes. So this is what we see the future going at. So this is pretty much what I wanted to show, and I did want to leave some time for questions. So let's go and see if we have any questions on the chat now or in the Q&A. Okay, so I don't see any questions. I guess this is good. Hopefully this made sense. So again, thank you everybody for joining. I hope you learned something about how to run AI workloads on Kubernetes. If you want to learn more, you can also find my LinkedIn at Guy Salton and then ping me. And if you want to learn more about AI for Kubernetes, you can also look up run.ai. And we're doing some interesting things here. So by that, I will end the session for today. Thank you all very much for joining. Bye-bye.